let's have it, no? So for this next set, no, so this will focus more, no, still on electric charges, but we will try to look into, no, that equation that we wrote just earlier, no, on the Coulomb's law for electrostatics made by Charles Coulomb, no. Now, Charles Coulomb, no, other than the Coulomb's law or principle that was attributed to him, his name, no, or his family name was also used as a unit of our electric charge, no. So similar to mass, for example. So for mass, we have kilogram, no, we have grams, no. So that unit, no, gram is maybe, no, we can equate it with our Coulomb, no. So that's the number of particles that are present, no, in our electric charge, no. By the way, no, one characteristic also aside from being conserved, no, charges have this quantized, no, quantized amount, no. So quantized is or quanta, no, is something like discrete. Kapag silingta nga discrete, no, these are numbers that comes in what, no, 0, 1, 2, 3, 4, no. So our charges kuno do mo na, no. So either wala charge or there's 1, 2, no, quantized, no. Maybe, no, we can think of it nga siguro wala sang half, you know, kung kwan siya, no, kung discrete bala ang number. So ang discrete is speaking of a number that is, no, a whole number, no. So it's either wala siya or ara isa, dua, tatlo. Like when we count people, no, how many people are in the bus, no? So we could never count that there's 2.5 people in the bus, no, because it's either 1 or 0, no. May ara tao or wala, no. Hindi pwede nga may tunga lang nga tao dito, no. So again, no, a quanta is something like that, no. So it's quantized, no, our idea of charges. Aside from, no, they are always conserved, no. We could never create charges them, no. So here's the French physicist Charles Augustin de Coulomb, no. That's in some text that we read, no. And again, where is that? Here is the equation that he formulated, no. So he eventually gives us a force of either attraction or repulsion, no? So this is the electric force. Maybe we can call it Fe, no? And there's a constant that we have, no, in this equation, and it's K, no? So we have Q1 for charge 1, Q sub 2 for charge number 2, and they are separated by a kind of a distance R, no? Now, again, no, in the case of our charges here, if you're dealing with positive charges, they will now push each other away, no? Push each other force, no? Each other charge, no? And they will move in the opposite direction, no? The same way when they are negative, both negative, no? But when they are of unlike charges, no, then they will tend to attract, no? So this is basically nature, no? So this is the natural law, no? But of course, no, not sometimes, no, not in our human relationships anymore, no? Sometimes we are in this day and age, no, we kind of maybe deviated from this law, no? So, but in the olden days, no, we see that to be true, no? Now, here is a Coulomb, no? It's the amount of charge that moves past a point, no, in 1 second, no, when a current is 1 ampere, no? So that's your Coulomb, no? Coulomb Q, no? And there's an equation there, I times T, no, that is denoted in terms of Q, no? Now, again, no, we will try to relate our understanding to that one, no, maybe in the future, no? Where why there's Q, no, equals to I times T, no? Well, again, no, we are not yet on the idea of current, no? So I there is for current, no, and T is for time, no, in seconds. Now, we have another unit for current there, no? Amo naman na yung unit nga ampere, no? So ampere second, no, IT is equivalent to a Coulomb, no? So 1 Coulomb, however, is a very, very large amount of charge, no? So we don't necessarily have, no, a charge that is exactly 1 Coulomb siguro, no? kadako na gid sinaguro nga charge, no? Usually, no, what we are dealing with are in micro, pico, nano, coulomb, no? So you'll notice that in the bottom of the slide here, no? So these are our ways of expressing, no, our charge Q, no? Either in pico, nano, or micro value, no? Now, for our value of K, no, K is equivalent to 9 times 10 to the 9, no? Newton meter square per Coulomb square, no? Now, here's an example of an expression, no, where we write, no, or solve a value of F, no? So here's our sample problem, no? Sample nga equation, no? So our unit of R must always be expressed in a meter, no? And I think 1 meter is a very, very long distance, no? So if you're considering a very tiny charge, no, very small charge, and the distance is brought not to a long, no, a very far distance, no, then maybe, you know, we could also experience a force there that is quite small, no? A very, very minimal amount of force. But if you bring the two charges very, very close to one another, then just imagine if they are both similar in sign, no? They have similar positive charge, no? Then maybe, no, they will try to push very, very hard, no, so that they will not be very close to one another, no? So again, no, the distance affects the amount of the force, no, in an inverse way, no? The square of the distance, no? So that's our Coulomb's law, ladies and gentlemen, no? Do you have a question about that? Now for our electron, no, an electron, no, is a very, very small amount of charge, no, and this is the number of coulombs present in our electron, no? So 1.602, no, times 10 to the negative 19, no? So that's a very small force, no, or small charge, no? So but again, no, that's the unit of an electron, no? So 1 e, no, or 1 electron, no? Others would describe our electron, no? We can write our value of our electron as 1e, no? And at times they write a minus sign at the top of the letter E, no? To denote that that's an electron, no? So they have a 1 electron, no? So that's 1.602, no? 10 to minus 19, no? Now therefore you can eventually know how many electrons are there in 1 coulomb, no? If you have a value like this, no, and you want to know how many electrons are present, no, then we can reverse the process here, no, and find, no, how many electrons are present actually, no, in 1 coulomb, no? So how many electrons are there, no, for 1 coulomb, no? Again, now to get that, I think you have to divide, no, 1 over 1.602 times 10 to the 19, no? So you have to make this denominator so that you'll be able to know, no, how many electrons are present in 1 coulomb of a charge, no? Now guys, no, can you divide for me now? 1 divided by 1.602, 10 to the 19. Now can you divide that value for me, no? So again, let's assume that that's correct. I think I find it quite lengthy, no, to ask that question, no? So but anyway, so 1 electron is a very small amount of coulombs of charge, no? But ang 1 coulomb, guys, it will involve, no, millions of millions, no, of millions of electrons, no, ang 1 coulomb. So that's why we basically, no, we do not deal with, no, when we show examples of forces, no, that we are dealing with 1 coulomb exactly, no, of a charge, no. So maybe, no, that's one thing that we have to bear in mind, no. Another one, no, is that we have 2 sets of materials, no, conductors and insulators. In our study of electricity, no, I think that's quite important, no, that there are types of materials that literally, no, allow, no, the flow of charges, no. So Not all materials will do that. No? Now, somewhere in between an insulator and a conductor, they also develop these materials called semiconductors. No? So semiconductors are materials that are either, no, at some point, no, they are conductors, and then at other points, no, same material can become an insulator. No? So these semiconductors are somewhere in between conductors and insulators, and they are used in the field of electronics. No? In the solid state or in the electronics field, no, we see this huge, we see this importance of these semiconducting devices, no, semiconducting materials, no. So if you have a material that can play both, no, insulator, and then you give it some ability, then it becomes a conductor. You can actually make it into a switch, no, an automatic switch. Now we see that no, a lot, no, in our computers, no, that we can generate, no, a series of ones and zeros, no, which is an equivalent of on and off. No? So we can have an on value as 1, an off value as 0, and we can generate a series of these ones and zeros, no, and make it into a code, no, into a kind of a signal, into some, it could mean and represent something. No? So that's the only language our computer understands, no? A series of ones and zeros, which we call as machine language. No? And then again, no, we can actually do that, no, and interact with our computer if, no, if we are able to produce that, no, automatically. No? And again, no, that's the function of our semiconducting devices. No? So again, no, the importance of conductors, no, and insulators. No? Now here is a picture of a use of our electrostatic steel. No? So what if, no, we don't have only 2 of them, no, but we have 3, no, and the 3 charges, no, happens to look like, no, look like this triangle. No? Now we can let 1 or 2 of them, no, to be of same sign, no, positive, and then we can let the other one be of opposite sign. No? And then naturally, no, some of them will now attract one another, and some of them will now repel one another. No? And because of this attraction or repulsion, no, that there would eventually be, no, a net direction of the force. No? So it will not simply be one line, no, that the charges are either pulling to one another or pushing each other away. But if we align them in this manner, no, then there would be a net force, no, that will now act on our object. No? So where is the net force here? No? Given that, for example, no, in B, no, we will try to find the net force. No? Now, if A is 1 microcoulomb, no, and B is also 1 microcoulomb, and they are both positive, then they will repel, they will push each other, no, away. No? So A and B will now have a repulsion. No? Now for B and C, no, so the one that is going on the right, no, so C is also, no, 1 microcoulomb as well. No? So between B and C, they will also repel. No? But question, no, what is the net force present on charge B? No? So if we look at the force present on charge B, no, then it is due to 2 forces. No? Now, if you look at B again, no, if we look at B, B will somehow, no, move downward like this. No, it will be pushed downward by virtue of A. No, because A will repel B. No? So the force present on B will be downward. No? Now, with respect to charge C, your charge B will also move to the left. So there would be force 1 that push it downward, no, slightly, no, at a certain angle downward, no, and because of C, it will be pushed also to the left. No? But question, where is now our net force? No, now our net force will be somewhere, no, in between these two. No, if you recall in your physics 1, no, that if there are two forces involved, then somehow no, that net force no, will be somewhere found in between them. No? Okay, so where will B eventually move? No? Maybe on the blue line. No? On the blue line, no, that's the direction of B, no, because that's the effect now of A, no, and C, no, on B. No? So B will not be simply moving left or downward, but no, it will be in between no, these two red lines. No, no but again, no, how do we measure the value no, of the force between A and B and C? No? So maybe we can apply Coulomb's law no, for that one. No? So maybe we can call this one as F2, the one that the force that is between B and C, and the force between A and B we can call it as F1. No? So if you have your F1 value and F2 value, you are now able to no get no the resultant here. No? Either no ano to ganyan method last time, you can draw the force. No? So you can use your tip to tail no? And eventually draw no your blue net force. No? So again, no, forces could be as complicated as this. No? So I'm just simply showing to you no, that you can let no, 3 charges come into play, or maybe even 4. No? So it's not just a simple single line no, that you will deal with 2 charges, no, but our analysis could even go as far as this, no, that we will involve our previous knowledge no, of resolving no, forces no, by their resultants. No? Okay, so I hope you are following. So we tried to calculate again no, our forces F1 and F2, and we said in terms of magnitude, they will simply have no this value. But if we will find the net force, then we have to consider the angle of each of the force there. No? Now, can you give me a value for F1 and F2 here? In terms of magnitude, no, in terms of magnitude, we are now able to calculate no, this F1 and F2 value 0.009 Newton. No? So it's a small value because again, no, we have a small charge and the distance is quite long, 1 meter. No? So you will end up with a small number of newtons of force. No? But in terms of the effect eventually of the movement, no, where charge B, no? So if this is A, this is B, this is C, no? Where will charge B move, no? So it will follow this blue line, no? Instead of these 2 red lines, no? Kay net siya ang value, no? So we can do that again, no? By maybe some graphical approach, no? If no, you forget already your that we call the method before as the component method. No? So we can also apply the component method in this case. No? So maybe no, one force is going 180 degrees no, left, and then another one is going it's moving you know, something like 240 no 240 degrees no. So this 240 degrees and 180 degrees will cost you a resultant over here now. So again you can use your component method if you want to no. Well that's with this one no? So I will just erase this no. So here's our eventual no component process no component method no. I think no it's not 1 Coulomb each no, but it's micro Coulomb no. So I think no, something is in error here no. Okay, this is in micro Coulomb supposedly no. So if they are 1 Coulomb each, then you will end up with this much of a force no. And again now we can have there the force, but the force that we consider no is acting on charge B no. So charge B no may have a different answer for this one no? Because this diagram is telling us no, I think of the charge in A no. Anong epekto sa charge A sa babaw no? And we are we are looking at no, a value kaina dito sa B. No? Well, you can see that in the slide that I attach here no, in our. So we can also deal with charges that are in line. No? So you could have 3 charges in line, or you could have something like letter L. No? And we can translate that no, into our understanding of no, charges by using our net force na concept. No? Okay, so that's our slide number 2. No, we will transfer to our next slide. No,